I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll prepare for calculus taking rational functions test questions. So in this particular question, we will determine horizontal, vertical and oblique asymptotes for two rational functions. You understand, for a rational function, horizontal and oblique, one of them could be there or neither. Perfect? Both cannot exist at the same time. Right. Well, you can pause the video, answer the question and then look into my suggestions. Let me thank all the viewers and subscribers for watching my videos and posting brilliant suggestions. Based on that, we have taken up this question and I hope many of you will benefit. Since last 15 years, we have been contributing and posting a video almost daily. We have crossed 20,000 videos with your cooperation and suggestions. Thanks. Feel free to contact me on the email address given and master this subject, as many students have done before. Great. Our student Akshat gets highest marks and the most prestigious Schulich Leader Award. You can be there. Join our classes and excel. Okay, so now let us first analyze the two given equations and then we'll solve them one by one. Clear? So let's do the first part, which is analysis. What do you suggest in A and in B? What kind of asymptotes do we have? Well, in A, we have degree of numerator and denominator is same, right? And that means we have horizontal asymptote. Correct? In B, degree of numerator is 1 high. So it is 1 more than denominator degree. And that means what do we have? Oblique asymptote. You get the idea. So clearly, we have identified that the first one has horizontal asymptote and the second one has oblique asymptote. Correct? Now here you also notice that we do have vertical asymptotes. Here also we have vertical asymptotes. But we could have whole also, right? Because that is something which we'll know about after factoring, correct? So now the second step is, we know first step, second step is factor to find wholes and vertical asymptotes. Clear? But first step is clear. So let's write down the asymptotes, horizontal and oblique, for the two now. So let's say A. To figure out the horizontal asymptote, what are we going to do? We'll see what happens when x approaches a large value, right? Positive infinity or negative infinity. Then what happens to y value? This is what we'll figure out. Some of you can write down the answer. It is the quotient of the leading coefficients, right? So some of you will write down the answer, which is, we have horizontal asymptote, which is basically equal to y equals to half, right? Now the question is, for others, prove it. So that is what we are going to do just now. So what we do here to prove it that we factor out x squared, which is common numerator and denominator. So we can write this as x squared common factor 1 minus 1 over x, right? So x divided by x squared will be 1 over x minus 2 over x squared, right? And in the second case, I take out x squared, so we get 2 plus 2 over x. Purposely, I did not factor 2 from the denominator this time. Now what you notice is that x squared and x squared cancel. Now think what happens if x approaches a very large value. In that case, 1 over x will approach 0, and similarly 1 over x squared will also approach 0. So that means these terms will approach 0, correct? So we can write this as f of x approaches, it is not equal to 1 over 2, right? For x approaching infinitely large value. So that is why we have a horizontal asymptote. So horizontal asymptote is what value a function approaches when x value is very large. It could be positive or negative. In this case, both sides, we get the same result, right? Which is half. So x approaches half in this particular case, as you can see. So we can say that the horizontal asymptote here is y equals to half. Clear? Now, let's look into the second equation and find the oblique asymptote. So in the second equation, the degree of numerator is 1 higher. So to find the oblique asymptote, you should divide the numerator by denominator, right? So we'll take part B. The equation is 2x squared minus 3x minus 5. We're going to divide this by x minus 5. So if you do that, what do you get? Well, it goes 2x times. Let me write 2x here. So we get 2x squared minus 10x. And when you take away, you get what? Minus 3, this becomes plus. We have 7x minus 5. Bring it down. And that goes plus 7 times, right? So 7 times will give us 7 times minus 35. And that is going to give us the remainder of 30. Remainder 30 suggests that when x is very large value, then this value is higher by 30, right? So we can now write f of x as equal to the quotient, which is 2x plus 7 plus 30, we still have to divide by x minus 5. So that becomes the division statement. Perfect? Absolutely clear? So we have an oblique asymptote, right? So we can write down now oblique asymptote. Whose equation is what? Whose equation is the quotient, right? So whose equation is this. So we have oblique asymptote, which is y equals to 2x plus 7. Is that clear to you? 2x plus 7. Now see, if x approaches positive, then the graph approaches from above. But when x is large negative value, then this becomes minus 30. So it will approach from bottom. So if you graph this, we're not getting into the details of graph, but if you graph it, in that case, you'll see that 2x plus 7 will be kind of like this. This is the line, which is 2x plus 7, correct? And the graph of this particular function will look like this. So it will be kind of like this on that side, and it is going to approach from bottom, right? Kind of like this. We do have at 5 a vertical asymptote, so that is what I'm leaving space here for. You get the idea. So that is how we do expect the graph. So I hope this is clear that when x approaches large, infinitely large value, then y approaches from above. But when x approaches negative infinity, y approaches the line from below, right? So that is what I wanted to emphasize in this particular case. So we have seen for both these functions the two things which are in this case oblique asymptote, and in the previous case we saw the horizontal asymptote. Now let's get back to this question and see, do we have a hole or a vertical asymptote? So let's get back to question number 1. So for that we need to factor both numerator and denominator. So now we'll figure out about vertical asymptotes and hole, right? I'm taking both the equations simultaneously so that you could appreciate what is going on, right? So this one, A, is basically, you can just factor this numerator as f of x equal to x minus 2 times x plus 1, right? And the denominator, 2x is common. So we get x plus 1. Now clearly, this x plus 1 and x plus 1 cancels, and therefore we could write this as equal to x minus 2 over 2x. The restrictions being that x is not equal to 0 and minus 1. Is that clear to you? So what do we have? So that means that at x equals to 0, we have a vertical asymptote. Let me write vertical asymptote at x equals to 0. But we have a hole at x equals to minus 1. You get the idea. Now sometimes we are interested in finding the coordinate value of the hole. So let's plug it in. So if I plug it in minus 1 here, what do I get? I get minus 1 minus 2 over minus 2, right? So that gives me minus 3 over minus 2, so which is 3 over 2. So we have a hole at x minus 1 where y value is equal to 3 by 2. Is that clear to you? So that becomes the hole for this particular function. Perfect. So we have done the factoring, which helps us figure out the vertical asymptotes, right? And the holes. Let us factor the other equation now. So the other equation is given to us as f of x equals to 2x squared minus 3x minus 5. So I'd like you to factor the numerator. You could split 3x as minus 5x plus 2x, right? 5 times 2 is 10. So let's do that. So we could write this as 2x squared minus 2 minus 5x plus 2x, that is minus 3x, right? And the denominator being x minus 5. So we could take x common. So we get 2x minus 5 plus 2x minus 5. And here we have x minus 5. And that gives you x times, let me factor 2x minus 1 first. 2x minus 5 times x plus 1 over x minus 5. Correct? So clearly, factors are not cancelling out. So here we have only a vertical asymptote which is at x equals to 5. Clear? So likewise, you can easily find that whether the equation has a hole or not. So equation has a hole when there is a factor in numerator and denominator which cancels out. If not, then the restriction becomes a vertical asymptote. Is that clear to you? Now with this in mind, I think what you can do here is analyze and graph both of them, right? So we could almost graph them. So can you graph these two functions? So in the first one, we have found that there is a horizontal asymptote which is 1 over 2, and we have a hole since x equals to minus 1 gave us 3 by 2, and there's a vertical asymptote which was at x equals to 0, right? So since we know that there is a vertical asymptote, we can draw this vertical asymptote, right? And we have a hole at minus 1, 3 by 2, right? So at minus 1 is positive. So we have on this side, we have a horizontal asymptote which is at half. So let me draw the horizontal asymptote at half. Let's say this is the horizontal asymptote. So this is at y equals to half, right? And here we have a vertical asymptote which is x equals to 0. The graph will be at minus 1 we have a hole, so it will be kind of like this. So I'm drawing it big, not accurate enough. You can always find the x-intercept. If I plug in x equals to 0, if I plug in y equals to 0, then we get the numerator, which we had factored out. You see that? When you had factored the numerator, x minus 2 in the numerator, right? So that would be 0 at 2. So that is the x-intercept, which is at 2, right? So that will be kind of like this, where this point is at 2. So this becomes the graph. This is the x-intercept of the function f of x, which we could actually write as x minus 2 over. So we got 2x common, right? Right. So that becomes the graph of this one. Now in this particular case, we got an oblique asymptote. So let me write down f of x once again from what we had got after division. 2x plus 7 plus 30, right? Over x minus 5. So 2x plus 7 is the oblique asymptote, which I'm drawing here. So this is 2x plus 7, y equals 2. Right? We have a vertical asymptote at 5. So that is the vertical asymptote at 5. Right? Now, so we have, as x approaches infinity, f of x is more than 2x plus 7 from above, right? So from above means it is going to go like this. You get the idea. But when x approaches minus infinity, then f of x is from below, right? So we write 2x plus 7 below, right? So this goes from here. You can find the x-intercept. X-intercept will be at 1, right? Since x-intercept is at 1, and when x equals to 0, we have y-intercept, which is at 1, right? So we can actually sketch this graph very clearly like this. You get the idea. So that is how the graph will look like. Now exact turning points you can find using calculus, right? So that is why we do have calculus involved. We are not getting in there. So with calculus, we can find the exact turning points and the actual graph. So let me make a note here in summary. That is, exact turning points are when the derivative of this is equal to 0, right? So for that, we'll need calculus. So some of you who have already taken up calculus can actually provide the actual graph, which will look something like what I'd drawn. But our focus in this particular exercise was only to determine the asymptotes, right? So we worked on the asymptotes and we found that we have horizontal asymptote, vertical asymptote, and a hole in this particular case. And here we have oblique asymptote and vertical asymptote. Perfect. You know the reasons, which is same degree in numerator and denominator leads to horizontal asymptotes. One more degree than the denominator gives you oblique asymptote. Perfect. For vertical asymptote, you know denominator should be 0, and for whole we have a common factor. Make sense? So that is how we could actually determine these. But in addition, we also analyzed behavior near asymptotes. Perfect. I hope you find it interesting and useful. Feel free to write your comment, share your views. If you like and subscribe to my videos, that would be great. And if you want to learn from me, you can always send an email on the address given or contact us on the website. Thank you and have a great day. Bye.